In 1881, a Persian engineer named Mehdi Karimi documented a structure in the desert city of Yazd that kept interior rooms at 68 degrees Fahrenheit while the outside air boiled at 115. No electricity, no refrigerant, no moving parts, just clay, wind, and a forgotten geometry that modern HVAC companies have spent the last 70 years pretending doesn't exist. The Department of Energy quietly studied this same design in 1978, buried the report in a technical archive at Lawrence Berkeley National Laboratory, and never spoke of it publicly again. Why? Because if every homeowner in America understood that a $30 tower built in a single afternoon could slash their cooling bill by 60 to 80%, the $430 billion global air conditioning industry would collapse before Labor Day. And the strangest part of this whole story isn't the tower itself, it's who first taught it to the West, and why their names were scrubbed from the engineering textbooks. Stay with me, because by the end of this video, you'll know exactly how to build one yourself, what materials to use, and the one mistake almost everyone makes that ruins the cooling effect entirely. Let me take you back to the summer of 2021. A retired mechanical engineer in Tucson, Arizona named Robert Hollis posted a thread on Reddit's Homesteading forum that quietly went viral inside off-grid circles. Hollis claimed he had reduced his July electric bill from $412 down to $68, not by installing solar panels, not by buying a mini split. He built what he called a passive downdraft cooling tower in his backyard using terracotta pots, a length of PVC, burlap, and a small solar fountain pump he bought at a hardware store for $12. The total cost, including the pump, was under $35. Within 48 hours, the thread had over 4,000 comments. HVAC technicians flooded in calling it a scam. Engineers from Sandia National Labs quietly confirmed the physics were sound. And the post was eventually shadow removed from the front page of Reddit, though you can still find archived screenshots if you know where to look. What Hollis had stumbled onto wasn't new, it was ancient. The Persians called it a Badgir, which translates roughly to wind catcher. The Egyptians built versions of them into the temples at Karnak over 3,000 years ago. Archaeologists at the University of Cambridge published a paper in 2014 confirming that residential structures in Hyderabad, Sindh, dating back to the 14th century, maintained interior temperatures 25 to 30 degrees cooler than ambient outdoor conditions year after year, using nothing but evaporative physics and clever geometry. The principle is elegantly simple, but the execution requires understanding three specific variables that most modern do-it-yourself videos completely ignore, which is why 90% of people who try to build one of these end up with something that barely works. Here's how the science actually functions. Hot, dry air enters the top of a vertical shaft. Inside that shaft, water evaporates off a porous surface, usually wet cloth, unglazed clay, or burlap. Evaporation is an endothermic reaction, meaning it absorbs heat from the surrounding air. As the air loses heat, it becomes denser. Denser air sinks. That sinking creates a natural downdraft that pushes cool, humidified air out the bottom of the tower and into the living space. No fan required. No compressor, no coolant. The tower itself is the engine. The fuel is water, and at the rate of evaporation we're talking about, you'll use maybe 2 to 3 gallons per day during peak summer heat. That's less water than a single toilet flush per hour. Now here's where it gets interesting, and where most builders get it wrong. The tower has to be tall enough to create what fluid dynamicists call a stack effect. If your tower is under 5 feet, the cool air doesn't have enough vertical drop to build downward momentum, and the whole system stalls. The sweet spot, based on testing done by researchers at Arizona State University in 2019, is between 6 and 8 feet tall, with an internal diameter of roughly 10 to 14 inches. Too narrow and you choke the airflow, too wide and the air column breaks up before reaching the bottom. Get those dimensions right, and you can produce a continuous flow of air between 20 and 30 degrees cooler than the outside temperature, moving at roughly 100 to 150 cubic feet per minute. That's enough to cool a 400 square foot bedroom to genuine comfort levels even when it's 110 degrees outside. The materials list is almost insultingly simple. You need a length of 6 to 8 foot PVC pipe with a 10 to 12 inch diameter, which runs about $18 at any hardware store. You need roughly 4 feet of natural burlap or unbleached cotton cloth, which costs around $4. You need a small, submersible fountain pump rated for 100 gallons per hour, which you can find for $8 to $10 online. You need a 5-gallon bucket to serve as the water reservoir at the base, which most people already have lying around. And you need about 10 feet of 1/4-inch vinyl tubing to circulate the water from the pump up to the top of the tower, where it slowly trickles down through the cloth lining. That's it. Total cost, depending on what you have on hand, lands somewhere between $28 and $36. The assembly takes about 3 hours if you've never done it before. You drill a small hole near the top of the PVC pipe for the tubing to enter. You line the inside of the pipe with the burlap, securing it at the top with a hose clamp or zip ties. You feed the tubing up through the hole and clip it to the rim so water trickles down the burlap evenly. You place the bottom of the pipe over the bucket with the pump submerged inside, and you cut a small opening at the base of the bucket 6 inches above the water line for the cooled air to exit. That exit needs to point either into your home through a window adapter or directly at the area you're trying to cool. Plug in the pump. Fill the bucket with water, and within about 15 minutes the tower reaches steady-state operation. You'll feel the cool air pouring out the bottom like an invisible waterfall. There's a man in New Mexico named Daniel Reyes who's been documenting his tower setup on a small YouTube channel for the past 2 summers. He posted infrared thermal images showing his living room at 72 degrees while the exterior thermometer read 104. His electricity bill, which used to run over $300 in July, came in at $47 last summer. He's run the tower continuously for over 800 hours without a single mechanical failure because there's almost nothing to fail. The pump is the only moving part, and even those run for years before needing replacement. But here's the catch that nobody talks about, and this is where the design gets serious. These towers only work efficiently in dry climates. If you live somewhere with relative humidity above 60%, evaporative cooling loses most of its effectiveness because the air is already saturated with moisture and can't absorb much more. That's why these structures originated in Persia, Egypt, and the American Southwest. For folks in Phoenix, Albuquerque, Las Vegas, El Paso, Reno, Denver, Boise, and most of inland California, this design will work spectacularly. For folks in Houston, Miami, New Orleans, or Atlanta in mid-August, you'll get some cooling but not the dramatic drops we're talking about. There are modifications that help in humid climates, involving desiccant beds and 2-stage cooling, but those add complexity and cost, and they're a whole separate conversation. Now, if you've made it this far, you already understand more about passive cooling than 99% of homeowners, and probably more than half the HVAC contractors out there charging $6,000 to install systems that do half the work. And if you want the full blueprint, every measurement, every material specification, every wiring diagram for the optional solar pump upgrade, the desiccant modifications for humid regions, the wind-assisted variations that don't even need electricity, and the dozens of other off-grid systems the Amish and Old World builders have used for generations to heat, cool, and protect their homes without depending on the utility companies, it's all laid out step by step in the manual. Link in the description below. Everything I'm covering in this video is just the surface. The manual goes into the structural reinforcements, the airflow calculations, the regional adaptations, and the small refinements that take a basic build from working to genuinely transformative. Let's talk about why the air conditioning industry has worked so hard for so long to keep designs like this out of mainstream conversation. In 1936, a Texas inventor named Oscar Palmer Jr. filed a patent for what he called a residential evaporative tower. The patent was approved, but Palmer struggled for years to find a manufacturer willing to produce his design at scale. Carrier Corporation, which had been founded in 1915 and held a near monopoly on mechanical refrigeration, allegedly approached Palmer in 1939 and offered to buy his patent outright. According to court documents that surfaced during an unrelated antitrust investigation in 1952, Palmer refused. Within 18 months, his small manufacturing operation in Lubbock had been undercut by aggressive pricing from larger competitors. His retail partnerships dried up, and he filed for bankruptcy in 1942. His patent expired without ever being commercialized, and the design fell into obscurity. This pattern repeats throughout the history of passive cooling technology. In 1954, a research team at the University of Arizona built a full-scale demonstration home using nothing but passive solar heating in winter and a wind tower cooling system in summer. The home maintained temperatures between 68 and 76 degrees year-round with zero mechanical heating or cooling. The study was published in a regional architecture journal, generated brief excitement among a handful of architects, and then disappeared from the public conversation almost entirely. By the late 1960s, central air conditioning had become a standard feature in American homes, marketed not just as comfort but as a marker of modernity and success. To suggest that a clay and cloth tower could outperform a refrigerated system even in specific climates became almost socially unacceptable in the architectural community. There's a fascinating thread on X from a former Honeywell engineer named Carl Whitman, who retired in 2018 after 32 years in the HVAC industry. Whitman has been quietly posting about the suppression of passive cooling research, and one of his threads got significant traction last summer. He described internal meetings in the early 2000s where engineers were specifically discouraged from publishing research on evaporative and radiant cooling systems because, in his words, the entire business model depends on selling sealed, refrigerated systems with consumable parts and service contracts. A simple tower with no moving parts and a 50-year lifespan is the opposite of a profitable product. It's a one-time purchase that pays for itself in a single summer and then costs almost nothing to maintain. The data backs up everything Whitman said. The average American household spends roughly $2,000 per year on cooling, according to figures from the Energy Information Administration. In hot, dry states, that figure jumps to $3,000 or more. A properly built passive downdraft tower in the right climate can reduce that figure by 60 to 80%. That's potentially $1,800 per year, every year, for decades. Over a 20-year period, you're looking at savings approaching $40,000 from a $30 build. No wonder the industry would prefer you didn't know about it. Let me walk you through a few of the upgrades that take a basic tower from good to extraordinary. The first is what's called a charged thermal mass base. Instead of just a 5-gallon bucket of water, you place the tower over a much larger reservoir, ideally something like a 50-gallon drum or a buried concrete cistern. The greater the mass of water, the more stable the cooling output, because water has a tremendous heat capacity. A small bucket warms up over the course of the day and gradually loses effectiveness by late afternoon, which is exactly when you need cooling most. A large reservoir, especially one that's partially buried, stays cool around the clock and lets the tower perform at full capacity even during the brutal evening heat. The second upgrade is what the Persians figured out 1,000 years ago, and it's called wind capture. Instead of letting the air drift passively into the top of the tower, you build a small directional scoop or cowl on top, oriented to face the prevailing wind. This dramatically increases the airflow rate through the tower without requiring any fans or electricity. In windy regions like West Texas or eastern New Mexico, a wind capture cowl can double the cooling output, and the entire modification costs about $5 in sheet metal and screws. The third upgrade involves earth coupling. By running the air intake through a buried PVC pipe, 20 to 30 feet long, 4 feet below ground level, the incoming air is pre-cooled by the constant subterranean temperature of 55 to 65 degrees. By the time that air reaches the tower, it's already significantly cooler than the surface air, and the evaporative process brings it down even further. This is the technique that the Hyderabad builders used in the 14th century, and modern testing has confirmed it can achieve outlet temperatures as low as 62 degrees even when the surface temperature is over 100. The earth-coupled tower is a complete game-changer in extreme heat zones, and the materials add maybe $40 to the total cost. A man named Anthony Foreman in Bakersfield, California, posted videos last summer of his earth-coupled tower setup producing 64-degree air during a 108-degree heat wave. His monthly electric bill in August came in at $31. He has 2 small children and runs the cooled air into both of their bedrooms through insulated ducting. His comment section is full of skeptics demanding proof, and Foreman has patiently responded by posting infrared images, thermometer readings, and electric bill screenshots. The evidence is overwhelming, and yet the conversation around this technology remains stubbornly absent from mainstream home improvement media. There's a reason for that, and it's worth understanding. Home improvement television, home improvement magazines, and home improvement YouTube are all funded primarily by advertising dollars from the same companies that sell central air conditioning, mini splits, and refrigeration equipment. You will not see a feature on This Old House about building a passive cooling tower for $30. You will not see Bob Vila demonstrating an earth-coupled wind tower. The economics of the industry simply do not allow it. The information is suppressed not through some grand conspiracy, but through the quiet, persistent pressure of advertising relationships and the structural incentives of an industry that profits from complexity and continuous consumption. A few practical notes before we wrap up. The pump you use matters more than you might think. Cheap pumps burn out quickly, especially when running 12 to 16 hours a day during peak summer. Spend a few extra dollars on a quality unit rated for continuous operation. Look for one with ceramic bearings if possible. The burlap or cloth lining inside the tower will eventually accumulate mineral deposits from the water, which reduces its absorbency. Plan to replace it every 2 to 3 months during heavy use, or soak it overnight in a vinegar solution to dissolve the buildup. Use distilled or rainwater if you can, because tap water in hard water regions will mineralize the cloth much faster. Position matters too. The tower works best when placed in partial shade, ideally on the north or east side of your home. Direct sun heats up the PVC and reduces efficiency. If you can shade the tower with a simple lattice or even a beach umbrella, you'll squeeze noticeably better performance out of it. And if you're routing the cooled air into your home through a window, use foam weather stripping around the duct to prevent hot outside air from leaking back in. Air sealing is the most commonly overlooked detail, and it can make a 10 to 15 degree difference in interior temperature. One last thing about safety. The water in the reservoir should be changed at least once a week, and a small amount of food-grade hydrogen peroxide or a drop of bleach should be added to prevent bacterial growth, particularly Legionella, which can develop in standing warm water. This is the same precaution recommended for any evaporative cooler, and it takes about 10 seconds. Skip this step and you're potentially aerosolizing bacteria into your living space. Do it consistently and the system is as safe as any commercial swamp cooler on the market. So, to bring this full circle, the secret that the Persian builders understood, that the Egyptian temple architects exploited, that Oscar Palmer tried to commercialize and got crushed for, that the University of Arizona quietly demonstrated and then watched fade from public memory, is this. Cooling a home does not require complicated machinery, refrigerants, or four-figure equipment purchases. It requires understanding 3 variables, sourcing $30 worth of materials, and spending one afternoon assembling them correctly. The physics have not changed in 3,000 years. What changed is who profits from your discomfort and how much they're willing to spend to make sure you never learn the alternative. If this is the first time you've seen something like this, you're going to find that once you build one and feel that 25-degree drop in air temperature with your own skin, the entire mythology around modern cooling starts to fall apart. You'll start questioning every other utility-dependent system in your home. You'll start looking at heating, water, electricity, food storage, and shelter through a completely different lens. That's exactly what the manual is built around, and it's exactly what generations of self-sufficient builders, from the Persians to the Amish to the desert pioneers of the American Southwest, have always understood. Comfort doesn't have to come from a meter. Sometimes it just comes from clay, water, and a little bit of forgotten knowledge. Build the tower, test it for yourself, and next time you walk past your thermostat with the AC roaring, remember that the device on your wall is not a necessity, it's a habit. And habits can be broken one $30 tower at a time. Consider what happened in Yazd, Iran, a city that sits at the edge of the Dasht-e-Kavir Desert, where summer temperatures routinely climb past 110 degrees Fahrenheit. For roughly 2,000 years, the residents of Yazd built their homes around structures called badgirs, wind catchers, tall rectangular towers rising from rooftops that funneled prevailing breezes down through clay-lined shafts. Inside many of these homes, the descending air passed over an underground qanat, a hand-dug water channel that ran beneath the city for miles, fed by snowmelt from the sheer Ku Mountains 40 kilometers away. By the time that air reached the living quarters, it had dropped 20 to 30 degrees. Families slept comfortably through nights when the outside surface of their walls was still hot enough to fry an egg. The oldest documented Badgir in Yazd dates to around 1300 CE, but archaeological evidence from nearby Persepolis suggests the principle was already being applied during the reign of Darius the Great, around 500 BCE. That's 2,500 years of continuous cooling technology running without a single watt of electricity, without a single ounce of refrigerant, and without a single service call. Now, consider what happened to that knowledge in the United States. In 1902, a 25-year-old engineer named Willis Carrier installed the first modern electrical air conditioning system at the Sackett-Wilhelms Lithographing and Publishing Company in Brooklyn, New York. The system wasn't designed for human comfort. It was designed to control humidity so that color printing plates would align correctly. It used coils filled with cold water to condense moisture out of the air. Within a decade, Carrier had figured out that the same principle could be sold as a luxury item to movie theaters, then department stores, then office buildings. By 1947, when window units became affordable for middle-class families, fewer than 74,000 American homes had air conditioning. By 1960, that number had climbed to over 6 million. By 1980, more than half of all American households had some form of mechanical cooling. Today, the figure stands at roughly 90%. In the span of 3 generations, an entire civilization went from understanding evaporative cooling as common knowledge to treating it as an exotic curiosity. The cost of that transition is staggering. The U.S. Energy Information Administration reports that air conditioning accounts for approximately 12% of total household energy expenditure nationwide, and in southern states like Texas, Florida, and Arizona, that figure routinely exceeds 27%. The average American family spends between $400 and $900 per year just on cooling. Multiply that across 128 million households and you arrive at a figure north of $76 billion annually, flowing from ordinary people directly into the accounts of utility companies, equipment manufacturers, and the petroleum industry that supplies refrigerants and the natural gas that fires the power plants. $76 billion every single year for something that the residents of Yazd accomplished with clay pots and gravity. And the costs aren't just financial. The refrigerants used in conventional air conditioning, hydrofluorocarbons like R410A and the older R22, are greenhouse gases hundreds to thousands of times more potent than carbon dioxide on a per molecule basis. When an HVAC technician evacuates an old system, when a window unit cracks in a landfill, when a compressor seal fails after 8 years of service, those refrigerants leak into the atmosphere. The Intergovernmental Panel on Climate Change has identified HFC emissions as one of the fastest growing contributors to warming, and the Kigali Amendment to the Montreal Protocol, signed in 2016 and ratified by the United States in 2022, was specifically designed to phase them out. But phasing out refrigerants doesn't mean replacing them with clay towers. It means replacing them with newer, slightly less damaging refrigerants, manufactured by the same companies, distributed through the same channels, requiring the same service contracts. The business model is preserved, only the chemistry shifts. Compare that to the tower you just built. Its refrigerant is water. Its energy source is whatever breeze passes through the room, or at most a small fan drawing 12 to 20 watts. Its byproducts are humidified air and, eventually, a slightly damp pile of clay that can be returned to a garden bed. There is no service contract, there is no compressor to fail, there is no copper to corrode, there are no fins to bend. When a part breaks, you replace it for a few dollars at a hardware store. When the entire tower has lived out its useful life, perhaps 8 or 10 years from now, you take it apart with your hands and the materials return to the earth they came from. Now, I want to address something directly, because anyone who has spent time in genuinely humid climates is already thinking it. Evaporative cooling has a limitation, and that limitation is humidity. The drier the air, the more cooling potential it has. because dry air can absorb more water vapor before reaching saturation. In a desert environment like Phoenix or Tucson, where summer relative humidity often drops below 15%, an evaporative cooler can produce that full 25-degree drop with almost no loss in efficiency. In Houston, in August, where humidity routinely exceeds 80%, the same device will struggle to produce more than a 5 or 6-degree drop, and it may actually make the room feel worse by adding moisture to already saturated air. This is not a flaw in the technology, it is a feature of physics, and the Persians understood it. Yazd is dry. The Sindh region of Pakistan, where similar techniques developed independently, is dry. The American Southwest, where settlers in the late 1800s built swamp coolers from burlap and water-soaked frames, is dry. If you live east of the Mississippi River in summer, you'll need to think about this differently. You'll need to combine evaporative cooling with dehumidification, or use it during the cooler morning and evening hours when humidity drops, or pair it with cross-ventilation strategies that move saturated air out of the building. The tower is not magic. It is a tool, and like every tool, it works best when matched to the conditions it was designed for. But here's what's interesting. Even in humid climates, the tower can dramatically reduce your dependence on mechanical cooling during shoulder seasons. Those weeks in May and September when temperatures are warm but not extreme, when running a central AC system costs you $8 to $15 a day for marginal benefit. Those weeks add up. In Atlanta, for instance, there are typically 60 to 70 days per year when outside temperatures fall between 78 and 88 degrees and humidity is moderate, perfectly suited for evaporative supplementation. Cutting AC use on even half those days saves the average household between $100 and $180 per year. The $30 tower pays for itself within a single shoulder season, then continues paying dividends for the next decade. Let me give you a name to remember: Ashok Gadgil. In 1996, this physicist at Lawrence Berkeley National Laboratory developed a low-cost water purification device for the developing world. A few years later, working with the same philosophy of low-tech, high-impact engineering, he and his team began studying traditional Indian cooling structures, including the matka, a clay pot used for storing drinking water that keeps its contents 15 to 20 degrees below ambient temperature through evaporation. Gadgil and his colleagues documented the physics, quantified the performance, and published their findings in peer-reviewed journals. The same physics that cools a matka in Rajasthan is the physics that cools the tower you've just built. This isn't folk wisdom dressed up in scientific clothing. It's documented, measurable, repeatable engineering, and it has been validated by some of the most rigorous research institutions in the world. The reason you haven't heard about it isn't that it doesn't work. It's that nobody profits from teaching it. Think for a moment about the Amish communities of Lancaster County, Pennsylvania, and Holmes County, Ohio. These are people who, by religious conviction, have largely opted out of grid electricity. Their summers are hot, their humidity is substantial, and yet they live, work, and raise families through July and August without window units, without central air, without compressors humming on every porch. How? Deep porches that shade the south and west walls of the house, white-painted exteriors that reflect rather than absorb solar radiation, high ceilings with transom windows that allow hot air to rise and escape, root cellars dug 6 feet into the earth where temperatures hold steady in the mid-50s year-round, providing a natural refuge during the worst afternoon heat. Hand-pumped water that stays cool from the depth of the well, used for soaking towels and cloths placed at open windows. Strategic landscaping with deciduous trees on the south side, providing summer shade but allowing winter sun. And yes, on the hottest days, evaporative cooling principles applied through wet sheets hung in doorways and damp cloths draped over fans powered by 12-volt batteries charged from windmills. These aren't quaint customs, they're a fully developed alternative cooling infrastructure, refined over 400 years, operating successfully across hundreds of thousands of households today. The same is true of the desert pioneers of New Mexico, Arizona, and West Texas. Adobe construction, which dominated southwestern building from the 17th century until the post-war housing boom, leveraged thermal mass to absorb daytime heat and release it slowly at night. Walls 18 to 24 inches thick stayed cool through the hottest hours, while small north-facing windows minimized solar gain. Courtyards with central fountains created microclimates of cool, humid air in the middle of otherwise scorching landscapes. The Pueblo peoples were doing this 1,000 years before Spanish colonists arrived, and the Spanish refined the techniques further. Then, in the span of about 30 years between 1950 and 1980, almost all of it was abandoned. Builders switched to stick frame construction with 2x4 walls, single-pane aluminum windows, dark asphalt roofs, and central AC ducted into every room. The new houses cooked in the sun and then cooled themselves at fantastic electrical expense. The old houses sat empty or were demolished. A working technology was replaced by a less efficient one because the new one had a sales force and the old one didn't. This is the pattern you have to see clearly if you want to understand why your electric bill looks the way it does. It's not that better technology displaced worse technology. In many cases, it's the opposite. Worse technology, more energy intensive, more financially extractive, more dependent on global supply chains and grid infrastructure, displaced better technology because it could be patented, manufactured, marketed, and sold. The tower you built cannot be patented.